Quantum superposition. In the classical sense, a coin can land on either heads or tails. However, in the realm of quantum mechanics, particles can exist in a superposition, a state in which they are effectively both heads and tails simultaneously, at least until an observation is made. This phenomenon is not merely a matter of uncertainty regarding the outcome. Rather, the particle genuinely occupies multiple states at once. Such a peculiar occurrence challenges traditional logic and prompts a re-evaluation of our understanding of reality. To comprehend superposition, it is essential to recognize the probabilistic nature of the quantum world. In classical mechanics, the behavior of objects can be predicted with accuracy if their initial conditions are known. For instance, when a ball is thrown into the air, its trajectory can be calculated precisely. In contrast, particles such as electrons or photons in quantum mechanics do not adhere to specific paths. Instead, their behavior is described by a wave function, a mathematical representation that encompasses all potential states a particle may occupy. When we assert that a particle is in a superposition, we indicate that its wave function embodies multiple states at once. A well-known thought experiment that exemplifies this idea is Schrödinger's cat. In this scenario, a cat is confined in a sealed box with a vial of poison that will be released if a quantum particle within the box decays. The state of the particle, whether it has decayed or not, is determined by quantum superposition, meaning it exists in both states until an observation is made. As a result, the cat is considered to be both alive and dead until the box is opened and the situation is observed. While this thought experiment may seem absurd, it highlights how quantum superposition can lead to paradoxical outcomes when applied to larger objects. The principle of superposition was first articulated in the early 20th century as physicists sought to understand the behavior of particles at atomic and subatomic levels. Experiments involving light and electrons, particularly the double-slit experiment, demonstrated patterns that could only be accounted for if particles behaved as waves. When electrons are fired individually through two slits, they produce an interference pattern on a detector screen, a clear indication of wave-like behavior. This pattern arises only when the particles are in a superposition, effectively passing through both slits at once. Quantum superposition is not merely a theoretical concept. It has been confirmed through numerous experiments. For example, in 2010, researchers at the University of California successfully created a superposition state in a small metal paddle, an object visible to the naked eye. While not as large as Schrödinger's famous cat, this experiment illustrated that superposition extends beyond the microscopic domain and suggested a connection between the quantum and classical realms. However, the question of what occurs to a superposition upon observation introduces one of the most enigmatic aspects of quantum mechanics. According to the Copenhagen interpretation, the act of measurement causes the wave function to collapse, compelling the particle to adopt a specific state. Prior to measurement, the particle exists within a cloud of probabilities, but observation narrows it down to a single outcome. This raises significant inquiries. What defines an observation? Does consciousness influence this process, or can any interaction with the environment lead to the collapse of the wave function? The interplay between superposition and measurement has practical ramifications in areas such as quantum computing, where quantum computers utilize qubits that can exist in superpositions of 0 and 1, in contrast to classical bits that are limited to being either 0 or 1. This property enables quantum computers to execute numerous calculations at once, significantly enhancing their potential for specific tasks. For instance, superposition allows quantum algorithms to factor large numbers or search databases at an exponentially faster rate than classical algorithms. Additionally, superposition is crucial in quantum cryptography, providing unparalleled security for communications. In protocols such as quantum key distribution, The superposition states of particles are utilized to encode information. Any attempt to eavesdrop disrupts the superposition, making any tampering detectable and ensuring secure communication. One of the most fascinating applications of superposition is found in the field of quantum biology. Some researchers suggest that phenomena such as photosynthesis and bird navigation may involve quantum superposition. In photosynthesis, for example, superposition could facilitate the efficient transfer of energy through a plant's light-harvesting complexes by allowing it to explore all potential pathways simultaneously. Similarly, certain bird species are believed to leverage quantum effects in their visual systems to sense the Earth's magnetic field, which aids in their navigation. However, quantum superposition also prompts numerous questions. Why do we not observe superposition in our daily lives? The answer may be attributed to a phenomenon known as decoherence. When a quantum system interacts with its environment, the superposition states become entangled with the numerous particles in that environment. This interaction effectively suppresses the superposition, rendering it unobservable in macroscopic systems. Decoherence elucidates why quantum behavior is generally restricted to microscopic scales and explains why Schrödinger's cat would not realistically be both alive and dead. The many worlds interpretation of quantum mechanics presents an alternative perspective, positing that every possible outcome of a quantum event occurs in a distinct branching universe. In the scenario of Schrödinger's cat, the cat exists alive in one universe and deceased in another. While this interpretation circumvents the necessity for wave function collapse, it presents a perplexing notion. An infinite array of parallel realities, each representing a distinct outcome of every quantum event. Quantum superposition also raises philosophical inquiries regarding the essence of reality. Is the quantum realm fundamentally probabilistic, or does it conceal a deterministic structure that remains undiscovered? The ongoing discourse between determinism and randomness carries significant implications for concepts such as free will, causality, and the very essence of existence. In the realm of cosmology, superposition provides valuable insights. It is believed that the early universe existed in a superposition of quantum states, with its development influenced by quantum fluctuations. These fluctuations have left traces in the cosmic microwave background radiation, which in turn has shaped the large-scale structure of the universe we observe today. Gaining an understanding of superposition in this context may yield clues about the universe's origins and the fundamental nature of space-time. The counterintuitive aspects of superposition also challenge our intuitions, prompting us to think beyond classical limitations. It encourages us to reevaluate the assumptions we often take for granted, such as the notion that objects possess definite properties, that time flows uniformly, and that reality exists independently of observation. By embracing the paradoxes inherent in superposition, we can attain a deeper comprehension of the universe's mysteries. Quantum superposition transcends being merely a scientific principle. It serves as a deep reminder of the intricacies of the universe and the constraints of human understanding. It unveils a realm in which particles can inhabit various states simultaneously, where observation influences reality, and where the distinctions between certainty and possibility become indistinct. This principle not only enhances our comprehension of quantum mechanics, but also fosters a sense of awe and curiosity regarding the essence of existence itself.